recording. This is 17.6, electric power. Today we're going to talk about electrical power and energy and how to power relates to charge. So power is the amount of energy per time being transferred through a wire. To find this, we're going to take the potential difference, which is the energy per charge, and multiply it by the current, which is the charge per time. So you'll see that your charge actually ends up canceling out, and you end up with energy per time, just like joules per second, like kinetic energy or potential energy. You can get power by doing energy over time. So we just take our two different energy and time type things that have to do with charge or potential difference and our current, and you'll see that your charges cancel. Yeah, it's People's ID, or BI. Okay, I see everybody has a blue cup, so here we go. The main equation that we're going to use for this is P equals IV. The P is kind of curly for you. I just write an R with P, but that's because we also have pressure and other things that are capital P. So they make it like a curly P. It's IV. How I remember this, and it's really terrible. Just remember, this is terrible. Is P equals IV. When I was in college, one of my big sister in the sorority always said contract the HIV, like it's something mean. So this one's contract the HIV, P equals IV. I know, it's really terrible, but you won't forget it. And you can substitute I for V over R, right? V equals IR, so you can substitute I and get this P equals V squared over R. Now, P is still measured in in watts. Power is still measured in watts, just like it was when we were using mechanical energy. Your current is in amps. Your voltage is in, your potential difference is in voltage, and your resistance is in ohms. Yes.
Is R still the same thing?
R is still resistance in ohms. Yes. All right, kilowatt hours. Kilowatt hours is something you can turn joules into. Most of the kilowatt hour stuff you'll see in the actual power industry itself. If you go out and look at your power meter, there'll be things in kilowatt hours. It's equivalent to joules. All they did was take kilowatts, right, watts, times time. So power times time is equal to energy. They just rearranged this equation to be PT equals E. Okay, good. Okay. So 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. You can easily do that by just putting seconds into hours and kilo into watts into watts. So that one's not really a big deal. Horsepower, though, is a new one. 1 horsepower is equal to 746 watts. And that one they tend to use a little bit, not too much.
Wait, so there's a chance we can see you on the exam?
Yes. Mm-hmm. Although I believe that if they were going to give it to you on the exam, they'll give you this conversion. That's not something I don't think that you're really going to have to know right off the top of your head. But it'll be useful for your homework, which is why I feel it's yes.
Where does this new horsepower come from?
It actually comes from one single horse. Just look a horse up to a cart, how much you could pull on average. It's the same idea. Where did the foot come from?
But I saw like on Reddit, because that's the most reliable source I know. The average horse outputs about 16.9 horsepower. Yeah.
I mean, I guess that's possible. I don't know that. I was told that 1 horsepower is how much a horse can pull.
How much is now?
I'll give it to you. But I don't know.
I'll look it up.
Yeah.
But yeah, you can look it up. Sure. I haven't heard the 16 horsepower one, but I wouldn't be surprised. Just like, was King Henry's foot really 12 inches, or was it just kind of like a standard?
So
I don't know. Because it could have been a pony that they put it on.
Or tails.
No, well, 16 would be. So I don't know. And I know that pulling is different than other type of thing. Like a horse can pull a lot more weight than we can carry.
Yeah.
So I don't know. But yeah, that's an interesting history. I assumed that it was 1 because that's what I was told. But yeah, go ahead.
14.9.
14.9. Do you know the history of it?
It says that but over longer periods of time, the average sort of is one piece. Not a second.
No, it doesn't say. Okay. Interesting. You guys can do a report on it and get back to me next week.
Can we do that for our
Fresh credit?
Yeah, can we do that for our
No, because I have to take the test for that, unfortunately. Like in the FSA, they're going to give you articles, so I can't.
Can we show you a list of articles we have sources? We just choose 2.
You guys want to supply the
I
articles?
just
Sure.
really want to write about horsepower.
Sure. Yeah.
Really?
Give me 2 articles and tell me what you want to do with them. They have to be informational and explanatory, and I'll make it work.
So what kind of
And you have to do it before this Thursday, because that's when you're running assignments. I need it like Wednesday so I can make copies.
I'm not going to be here Thursday for it.
It'll be on film. You can just print. Good? You're good? Okay. So energy transfer in the circuit. Remember that the electrons are actually traveling this way. Electrons. There's the weird one. Okay. But we say the current goes from positive to negative. This is a circuit diagram. This is what you'll be drawing in our next chapter. So this would be the wire.
Okay, according to the story. You didn't want to hear more?
One sec. Let me finish. All right. This is the battery, this uneven line. Notice that it has negative is the shorter and positive is the longer. This is a resistor. This is the thing that would be resisting that power, controlling kind of how much current and voltage are going on through this. And this little green thing down here is the ground, meaning that the extra electrons are headed to the ground. And this is why in most of your plugs you get the 3 prongs. That extra 3rd prong, sometimes it doesn't happen. And the one, on the bottom middle. Yeah, that's the ground. That puts the extra electrons in there. That's why the 3 prongs are safer than the 2 prongs. It's because if it gets any extra electrons, it goes right into the earth. Instead of like building up extra electrons and creating an electrical shock, which could be bad. All right. So imagine. Oops. Where'd I go? There we go. So imagine that this charge, this Q, is moving around the circuit from point A to B. So your electrons are marching along this direction. So we'd say the current is in the opposite direction of that flow, which is weird. And the circuit has to be closed. If you break the circuit, then the electrons, they don't have anywhere, they have no reason to be flowing through your wire. You don't have anything pushing them along. They just kind of stop where they're at. So as long as you have them connected, you get this downhill from negative to positive hill, and the electrons will roll down. If you break it, now you've made the hill like this. Now they just stop. see any red cups? We'll move on. Did you want to share the horsepower, Nina?
Oh yeah. It says the term horsepower was coined by James Watt, the goddess inventor and mechanical engineer renowned for his improvement of the steam. In the early 1780s, Watt and partner Matthew Boulton set out to sell their steam engine to the breweries of London, calculating that they would be likely customers, blah blah blah. In order to convince the breweries of the advantages of the steam engine, you needed a method to compare their capabilities relative to horses and the power source they were seeking to replace. The typical brewery horse attached to a mill that ground the mash for making beer walked in an endless circle with a 24-foot diameter, pulled with a force of 180 pounds, and traveled at a speed of 180.96 feet per minute. Watt multiplied the speed times the force and came up with 32,580 feet-pounds per minute. That was about 36,000 feet-pounds per minute, and the figure used today.
So that's what 1 watt is?
What?
Or 1 horsepower? So it's not necessarily a horse going in a straight line, it's a horse pushing a brand mass, the mash thing around.
And a
24.
specific
And a
horse.
specific
Yep.
Yeah, it is.
Which means they don't have to do much belt work.
So it could have been like a really big horse.
It could have been a donkey one
Yeah.
is going around in a circle like that. It's like a hot walker. Nothing.
So multiplying horse by 17.
Okay, interesting.
What's the difference between a milkshake and a nut? What's the difference between a shake and smoothie?
Smoothie has ice, milkshake has ice cream.
No, milkshakes have like dairy and ice cream, whereas smoothies have like fruits and vegetables.
But you put milk in the fruits and vegetables.
You can, but it's not the main ingredient.
Can we get back on topic?
Yeah.
Okay.
You mean on the topic smoothies?
Here we go. Power. Right now it costs about 0.05 for coal power per kilowatt hour, and about 0.06, so about 6 cents for solar power, about 5 cents for coal power. Isn't that interesting?
That's quite a lot.
This is what it says on my power bill. And it's interesting that coal power is a lot less expensive, but that is because of all the subsidies. Right? That's like their government messing with
I
things.
imagine this is the most fine.
Yeah. Okay, so 1 square meter of ground gets about it gets enough sunlight to power 10 100-watt light bulbs. So here's an interesting question for you. How much money is a year's worth of sunlight? And I gave you the surface area of the Earth to get started.
Okay, wait, but 1 square meter of ground, how much time is that?
It's power, so it's giving you energy per time.
And this was what? So that's energy over seconds? Or
Yeah, that'll be 100 joules per second.
Well, actually, wait. How much is the sun actually hitting of the Earth? Because isn't there usually like only half of it being?
Yep, so you have to cut the surface area in half. Yeah?
Well, the first one, does that just mean like cents per solar power supply having a power plant that uses solar?
It's per kilowatt hour, and it's by that's what I get charged on my power bill. And it tells you on your power bill like how many kilowatt hours came from solar power and how many came from coal power.
So it's like, if you buy your own panels.
Right, and then it would be free, and you can actually sell it back. In some states. So you have power equals energy over time. You have 6 cents per kilowatt hour. You have 1 kilowatt hour equals 3.6 times 10 to the 6 joules. Let me just double check and make sure I got that one right. Yeah, 10 to the 6. And you have 1 square meter is equivalent to 100, 10 light bulbs, 10 100-watt light bulbs. came up with a lot bigger number when I
I
did
know,
it.
that should be a lot bigger. Are you keeping in mind like millimeters squared?
You convert all the kilometers into whatever meters.
This is just like a huge conversion here.
I got like 2.2 times 10 to the 15.
I still got a bigger number than that, but that's closer to what I got.
Yeah, just
But I might have made a mistake. So I'm going to see what everybody comes up with, and then we'll do it on the board. Okay, let's look at this. How much power output do we get in 1 square meter? 1 kilowatt. Or for this one, 10 times 100, right? So our power in 1 meter squared is going to be 1,000 watts in 1 meter squared. Okay, then we have the surface of the Earth, this 510.1 million kilometers squared. We want half of that, since only half the Earth is lit at a time. I'll get my calculator for this one. Okay, we get the surface area of the Earth over 2.
Oh, that's a very big number.
Right? Kilometers squared. Good. Did I make a mistake, or is that okay? Watch my calculations, because I get lost. Does that seem right? 1, 2, 6, 7, 8. Yeah, because this is 8. Okay. Then we got to convert to meters squared. In 1 kilometer, there is 1,000 meters, and we got to square that. Right, so we get it into the squared portion. So take this number and multiply it by 1,000 squared. You get 2.55 times 10 to the 14. Now this should be in meters squared now. Good so far? All right. Then I need to multiply this up here, right? And this will give me the power output of the whole Earth.
With time, right?
No.
We can focus on time later.
Yeah, we'll do time in a second. Okay, so watts, and then this is meters squared, so this will be,
So it would be 2.55 times 10 to the 17. You just add 3 zeros to it.
yep. So this gets rid of this. So this is watts. This is how much power output the Earth has at any second. It's this many joules per second. Because watts is joules per second. And then we have this weird thing down here. 1 kilowatt hour times 6 cents. So we need to get this into, let's do kilowatt hours. Kilowatts? Kilowatt hours.
So,
How many kilowatt hours does it give it out per year?
so wouldn't it be multiplied by,
So we go back to what Nick said. If we want to convert this into kilowatts, it'd be 2.55 times 10 to the 14 kilowatts. Mark off 3 zeros. Because he said this is 1 watt, which is, or 1,000 watts is 1 kilowatt. Okay, so we're good on that one. So this is our power. Our time is 365 point, is it 15 or 25? 15 days. And we need to convert that to,
Is every 4 years?
okay, kilowatts, and we need to convert it into hours. So how many hours are in a year?
So times 24. Day would be on the clock.
Yep, I'm thinking something else. 1 day, 24 hours. So 365.25 times 24 gives you hours. So our power times time is energy. So kilowatts times hours is 4. Times 10 to the 18, this is kilowatt hours. And then we have 6 cents a kilowatt hour. So you could take this number, multiply it by 6 cents per kilowatt hour, and that'll take this out and give us our cost. There we go. 1.34 times 10 to the 17. Anybody got that kind of money?
No, but you could.
Did anyone see a mistake that I might have made? I know it said something. That's what you got. Okay. That's a lot of money. That's like beyond trillions, right?
That's 134
Yeah, because a trillion is 12 zeros.
Well, there could be having money.
Good luck actually.
It was actually a question on like an NPR thing. It said how much is a year's worth of sunlight worth, and they were trying to calculate it using like the is it called the GOP or something of a country. GEP, something, I don't know. I know those sort of political things going out of my brain. I don't remember them very well. I can remember. So I was like, let's take it from a physics point of view. If this is how much sunlight the Earth is collecting, if you could collect that much of the entire surface of the Earth, this is how much money it would cost to collect that sunlight in 1 year. If you could collect everything.
The only problem with that is that it would kill off all the trees and the Earth would get cold because you're collecting all
Well,
the
no,
sun.
because you could take them down.
You can make artificial sun.
You can have them raised above the earth.
Yeah, but then
The
the light
other,
would get through.
one of the other things that I've heard was creating these giant solar mirrors on either side of the Earth, like collecting all the extra stuff.
Then all that stuff would just get bounced back to the Earth. And
Although
dry.
really,
It would be
what
like
you want to do is
just
just surround the entire sun with a big sphere of solar panels.
And then all
There you go. Would
then
that be
all
like
the
that?
planets get cold.
Or just have our own little fusion sun going on Earth, right?
Like, did you guys hear about that?
So you put a bunch of mirrors on one side of the sun, and you move the solar system around.
Or just move the solar system, right? That sounds great. All right. So any questions about this? I thought it was kind of neat to do it. Lots of money. Okay. Question 1.
Where?
Right there. This one should be pretty easy for you. A 60-watt light bulb in a socket supplied 120 volts. What is the current?
I say